Okay, let's get going. We were talking about general principles leading to good design. Among those principles are the principles of divide and conquer we talked about, cohesion, which is grouping things together in a good way so that you can you understand the purpose of each component, each unit, and you don't have extraneous stuff in a unit. And then there's the notion of coupling. And in the context of coupling, we talked about several kinds, some kinds that you really must avoid. Okay, so content coupling is the coupling where you have one component or module that is actually be able to reach inside another one and make changes. That is bad and should be always avoided. Second kind we talked about was common coupling, which is basically the use of global variables, which tends to tie all parts of the system together. You want to generally try and avoid that unless there are specific circumstances in which it really is necessary. We talked about control coupling, which is the notion where you have one procedure or routine that is exerting a very strong influence over another. Or it could be one component that is sending messages that another one is dispatching and dealing with, as in the simple chat system where we had handle message from server that has a whole bunch of if-then-else statements. So anytime you see these large numbers of if-then-else statements or switch statements, you know that one component is controlling another. It's sometimes not avoidable, but we want to try and reduce the total amount of control that is exerted of one routine over another, perhaps by using polymorphism or some similar mechanism, maybe a lookup table. And then we move on to stamp coupling. Stamp coupling is, to some extent, unavoidable. We have to sometimes pass data structures from one procedure to another, or from one component to another. The idea is that we don't want to do it unnecessarily. Stamp coupling occurs when you have a complex data structure such as a class or a struct in C that you're passing in an argument list from one routine to another. And it's sometimes essential to do that. But we want to see if there are ways to reduce it. On slide 32, we have an example where we have a class emailer and a class employee. Emailer should be generic. If the emailer class, its job is to send emails, why do we need to always, when we have that class, have the class employee along for the ride? It would be better if we didn't couple emailer and employee together and allowed them to exist independently in independent systems. So the class emailer could be used for emailing in many kinds of environments, and the class employee could be used if there was no emailing involved. But as it's written right now, the send email takes an employee object, so they both have to exist together in whatever systems use either, or certainly whatever system uses email. The better approach is shown at the bottom of slide 32, where we instead use strings as the arguments to the send email method. If we do that, then all we're doing is taking advantage of data types strings, which are used in every single Java system. And so we don't have to worry about that kind of coupling to the string class, because it's always available. So this makes the emailer class a lot more flexible now. It can be used without having to have employees along with it. A second strategy for decoupling is to use an interface. Okay, what I can do, as is shown here, is I declare an interface. In this case, I'm going to call it addressee. In other words, the person to whom an email will be sent. And this is going to have the methods that would be used, getName, getEmail, as abstract methods in my interface. Then I can declare any class, such as employee, to be an implementer of addressee. Now, in my emailer class, I declare my argument of send email to be an addressee. I'm no longer tied to the employee class. Okay? Because I can just declare any old addressee as the person to whom I'm sending the email, and that could be implemented by other classes in other systems. Okay? I'm coupled to my addressee interface, but that's light, and that can be part of my emailing package. The key is I don't want to tie myself to an employee human resources type package. That's a silly coupling to do. I can tie myself to an addressee interface because that has to do with emailing anyway. All right? So, two different strategies for reducing stamp coupling. The key is to reduce it where reasonable. There are circumstances where I need to pass an employee from one method to another. If in my benefits management system I need to access all of the instance variables, all of the operations on employees, it would be valid for me to pass an employee from one part of that system to another. That's not a problem. It's still stamp coupling, but it's legitimate stamp coupling. What's illegitimate is where I really don't need to pass the full complex data structure because I don't need all the values, or all the data, or all the operations in the employee class in my emailer. I just need the name and the email address. I don't need the rest. So don't pass the data structure that has all the rest of it. Okay? The idea is coupling is essential. To some extent, we want to see if there are ways we can weaken it and reduce it. Okay? Any questions? The remaining kinds of coupling are also things which you have to do from time to time. Data coupling is passing arguments in general. So stamp coupling was passing complex data structure arguments. Data coupling is passing arguments that are things like ints and strings and chars and so on. The idea is again, don't pass unnecessary arguments. So stamp coupling, don't pass unnecessarily complex arguments. Data coupling, don't pass unnecessary arguments of any kind. So if you have arguments that are not being used in a procedure, then remove them from the argument list of the procedure. And the idea is that will reduce the complexity of each link, each coupling link between one procedure and another, or one class and another. Okay? There's obviously a trade-off between data coupling and stamp coupling. Stamp coupling says, well, you know, sometimes you need it, but you can get rid of it by adding arguments and passing, instead of an employee object, passing two string objects. Well, that increases the data coupling. But that's fine. That's a decision we make because stamp coupling tends to be stronger on average than data coupling. So even having two simple arguments in this case would be a better choice than having one unnecessary complex employee object that we don't really need to pass. Okay? But it would be silly to, in my call to the emailer, to pass the employee's home address and phone number and all those kinds of things, because the emailer doesn't use that data, so why pass it? Okay? So cutting things like that out would be a way to cut out the data coupling, or reduce the amount of data coupling. Routine call coupling. It basically is any time you have one routine or one procedure, one method calling another, anywhere in the system, it adds to the total amount of routine call coupling. If these routine calls cross the boundaries between classes or between packages, that's stronger, that's considered worse coupling. But even inside classes, even inside packages, we want to try and reduce the total number of method calls to the minimum that we really need. You've got to do some calling of procedures, but don't do unnecessary calls. So how can we get rid of calls that are superfluous? Well, the delegation pattern is one strategy. Okay, remember the delegation pattern says that I'm going to be calling my neighbor only, rather than calling all over the system. I'm just calling my neighbor. So that reduces the total amount of data coupling between classes. I still have my neighbors coupled, but I don't have calls all over the place from many different routines to many other different routines. I can often route my calls through one particular delegation call. Okay, so that's one strategy for reducing the total amount of routine call coupling. Another strategy is simply to call a routine that does more stuff rather than call a sequence of routines. Okay? So calling a routine that encapsulates a sequence could be useful. Various strategies. So the idea is that when you're doing designs, think about the coupling. Think, am I introducing large amount of coupling that will cause the system to be harder to understand. Other ways that I can cut this down a little bit. So delegation is a key way, but there are others as well. Along a similar vein, using data types that are defined elsewhere is a form of coupling. So if I have a package and I'm using data types that are defined in another package, I'm coupling my package to that other package. If that other package changes, then I might have to change myself. So before we start declaring data types that are variables that are of some package somewhere else, we want to think, do we really want to do this? Is this the only solution? It often is. It usually is. But nevertheless, we have to be aware that the more we do of that, the more coupling we have between the packages. Type use coupling, then, is similar to stamp coupling, but stamp coupling is more insidious. Stamp coupling is also the use of types, but types of the arguments of methods. Whereas ordinary type use coupling is using types for local variables, instance variables, things like that. Obviously, when you're defining associations, okay, association between one class and another, we said that you have to declare variables of the type of the class on the other side. So there's type use coupling going on there automatically, anytime you have an association. Right? One strategy for reducing type use coupling is to use interfaces. Okay, we saw that with stamp coupling as well. Interfaces will tend to reduce the amount of type use coupling we have to do. Any questions? Okay, so all these things, calling routines, using types, passing arguments, you have to do them, but be aware of their impact as you do use them. See if there are ways to simplify. Another thing we have to do is, in C++, use inclusions, or in Java, use import statements. We want to reduce the total number of these, however, because having too many can cause significant complexity. What happens in Java when you have an import clause? What the import clause says is, make available to me all of the classes available in an imported package, or make a class available if you're importing just a single class. If I import an entire package, then I can use the classes in that package. But I'm also exposing myself to the potential that that package might change. If that foreign package decides they're going to change the classes that are there, delete classes, add new classes that may clash with the names of classes in other packages, then I end up having to change my system. Even if I'm not using those other classes or packages. There's a tendency for people to say, well, I don't know what I'm going to be needing to, but I'm going to include package A and B and C and D just in case. Or import them just in case. That exposes me to potential changes in those included packages, even if I'm not actually going to be calling methods or using classes there. So the idea is, only import just those classes or packages I'm going to need. If I'm only using one class in a foreign package, import that class only. If I'm using a bunch of classes, I can import the entire package, because it's simpler to do that, but don't import classes egregiously that I don't need, or import all kinds of packages I don't need. Okay? That's the general rule. It's worse in C++ and C, because inclusion is stronger and causes more complex consequences than importing does. But even in Java, we have to watch out for it. Interestingly, when I was working at BNR, which is now part of Nortel, a number of years back in the 80s, we actually had a policy in my group that we would have in every single C file a single include statement that would include a file that included all of the other files, all the other .h files in the system. Okay, so effectively we were including everything. And the idea was that then I can just use any code from anywhere in the system without having to worry about including it from that point on, because everything's included. But that can cause havoc because people can make changes elsewhere in the system and impact me. Okay, so it was done to misguided, with a misguided objective of simplifying. Yes, it meant that every single file had just one include statement in it that looked the same, but I was opening myself up, our group was opening ourselves up to problems with maintenance later on, when things might need to change. And if things change, I have to look through all of the code everywhere to see the impacts. Okay? Any questions about that? Yeah.
Suppose somebody made a change in a package and you're not using that particular stuff in our thing, how would it affect us?
Okay, if somebody added a class in a package that you import, and that class has the same name as a class that you have in your package, then you have a name conflict. Okay, so you have to start qualifying things. You have to start saying package.name in order to de-ambiguate that. But if all of a sudden that name conflict appears unexpectedly, you have to change your code. Okay. And then the final type of coupling we'll look at is external coupling. External coupling is also necessary, just like importing and calling routines and using types. It's necessary, but we want to reduce the total number of places that do it. External coupling is the calling of operating system facilities or database system facilities, facilities in different systems. Okay? We don't want our system to be calling from all over the place. Okay? Just going to get away from this. We don't want to have our system, this part and this part and this part and this part all calling the operating system. Okay? If we do this, we have 4 different places that call the operating system, and then we want to target to a new operating system, we're going to have to change this and this and this and this. Whereas if what I did was I had one place that calls the operating system, then all I have to do is to change this. Okay? So this is a lower amount of external coupling. Before, these were all external couplings. Now these are internal, and we only have one external coupling in place. Okay? So we want to try and reduce the amount of external coupling. If you have hardware manipulation, do it in one place in your system. If you have operating system manipulation, do it in one place. Okay? If you're calling packages that are reused in reusable libraries, try and limit the number of places that actually make use of those libraries. It goes in tandem with the import coupling too. I'd be importing the library files in fewer places as well. But a lot of these things do go together. Any questions? Okay, so just to wrap up our discussion of coupling, along with cohesion, it is one of the fundamental principles leading to good design. In some of the principles coming up, we'll see that, well, in order to achieve reuse, you need to do low coupling and high cohesion as well. In order to improve abstraction, you have to do low coupling and high cohesion. So we'll move on to principle 4 then. Principle 4 says, keep the abstraction level as high as possible. We've talked about abstraction before in Chapter 2. We talked about it in the context of classes. We said classes are abstractions, methods are procedure abstractions, classes are data abstractions, operations are further abstractions, superclasses and interfaces are further abstractions. There are many kinds of abstractions. So this is a review, but it's in the list. It's principle 4 because every time you're doing a design, every time you're evaluating a design, you want to think, are there ways that I can improve the abstraction? Okay? Abstraction allows us to think in terms of the abstraction without having to worry about the details that are underneath it. So we get what's called information hiding. The notion that we don't have, as users of the abstraction, to worry about the details. So using an interface, I don't have to worry about the implementation. Using a superclass, I don't have to worry about all the methods and the subclasses. I just have to worry about the methods available in that superclass. Okay? Using a class to manage data, I don't have to manage the data myself. I just have to know that the data is being managed for me, and I know the methods that set and get instance variables, and that's it. Okay? So on slide 40 then there's a little bit of review from chapter 2 that I won't go into now. Just a reminder that there's lots of different kinds of abstractions associated with classes in the object-oriented context. Principles 5 and 6 also are review from before. Principle 5, increased reusability, was something we talked about in some detail in chapter 3. Okay, we said when you're designing a system, think of ways in which you can make each component, each method, each class more applicable to other contexts. The whole notion of frameworks was a big part of that. So, generalizing your design as much as possible. Making your design not dependent on specific details. Our discussion of stamp coupling, where we couple together the emailer and the employee class, is a classic example of bad generalization. It's much better to create a generic emailer that can do any kind of emails rather than an emailer that's only capable of emailing employees. Okay? So to create reusability, we want to generalize and cut out specializations that are unnecessary. We want to follow all 3 of the preceding design principles. So adherence to high cohesion will group things together so that the unit is more reusable. Reducing coupling will make sure that we don't have to drag along a lot of other stuff when we reuse, so it improves reusability. And abstraction also improves reusability because we can clearly see the overriding function of this reusable component at the abstract level rather than having to worry about the details. And simplifying in any kind of way you can think of, so that the reusers don't have to know any complexity, they just see a very simple chunk that is trivial to reuse. Okay? This is basically a review. You can see more in chapter 3 on this. And then the flip side is reuse where possible. Okay? It's complementary. Designing with reuse is complementary to design for reusability. So find libraries that do the job for you. Find facilities that do the job for you. I had an experience this weekend which you might find interesting. I was creating a complex algorithm for doing some mathematical analysis, and I was writing it in C. Okay? And then I said to myself, why am I writing this thing in C? Why didn't I just go into Microsoft Excel? And I can't do, unless I do Visual Basic programming, I can't do loops and things. But I have all kinds of other facilities in Excel that are already there, all kinds of built-in functions that I can reuse and random number generators and stuff like that. And so I just said, okay, I'm going to not do this in C, I'm going to do it in Excel as a spreadsheet. Okay? And that's a classic example of reusing code. In this case, a very sophisticated system that's already there. There are many other kinds of systems like that that you can reuse, though. All the stuff is already there for you. And remember this notion of cloning. Okay, we say reuse existing designs and code where possible, but avoid cloning. Don't set out to say, well, I'm going to copy this 60 lines of code from place A to place B, because then the bugs will be carried over into 2 places instead of 1. Okay? Still good advice. Interestingly enough, last week at the conference I was at, I had a long discussion with another professor who's had quite a considerable amount of experience in industry, and he was preaching, get rid of the clones, to some people he works with in industry. In fact, he worked for a company. And the company came back and said, we have really top quality software. It has lots of clones in it, but we have top quality software. And we have a policy that we're not going to get rid of the clones. Because if we start getting rid of clones, we have to open up our code and start making changes to the code. And the fact that we're making changes will likely introduce bugs. And so we're only going to respond to actual reports of bugs. If there's a report of a bug, we'll fix that bug. And that's all we'll do. We're not going to go out actively to get rid of clones. So the advice of not adding clones egregiously for no purpose is still good advice. But this was an interesting thought, that sometimes when you listen to your clients and your customers, and you realize, and you do cost-benefit analysis, you might realize that, well, if you're stuck with something like cloning or some other pieces of questionable design, it might be better for the overall quality of the system to not remove them. It was an interesting thought that it hadn't really occurred to me before. And it's an example of where you need to keep an open mind as you're thinking in terms of software engineering. And think about the high-level principles. The high-level principle of reducing defects, the high-level principle of always evaluating every decision you make in terms of cost-benefit analysis. And even though you have a principle that says clones are bad, keeping the clones might be better than opening up the whole system and changing it in a large way. Okay? But when you're just doing design from scratch, reuse existing designs where possible is still good advice, and avoid cloning is still good advice. Principle 7, design for flexibility. This principle really builds on a number of the other principles. Okay, so reducing coupling will improve flexibility. Flexibility basically means anticipating changes for future extensions, and reducing coupling allows us to plug new things in and adapt more easily because we don't have to worry about the impacts of our changes. Increasing cohesion also tends to improve flexibility because we can see what each thing does and we can replace modules more easily again. Creating abstractions, and again from the earlier principle, principle 4, will improve flexibility because it's easier to understand the system. The third bullet here, however, is something which is particularly focused on flexibility and doesn't harken back to the earlier points we made. Don't hard code things. Now, I did make this point very, very earlier on in the course when I talked about coding style. But it bears repeating at this point. Hard coding things definitely reduces flexibility. And what kind of things can we hard code? Well, you might hard code, for example, the company's tax number. Okay? Or the total number of management levels in the organization. Or the name of the company, the phone number of the company. Okay? All of these things are things which, if we hard code them, then if they change, and they might change, we then have to open up the system and change the code. Okay? Business rules. Rules that say that if you have a certain amount of money in this account, you've got to transfer that money to the other account. Well, sometimes you have to hard code things if they're complex logic, but if you can create these rules as data that gets read in, and you can change the data format to change the rules, that's more flexible than if you hard coded it right deep into your Java. Okay? Hard coding deadline dates is another example of trying to avoid any of these kinds of hard coding. Read things in as data, okay, rather than putting them as constants right in your program. Leave all options open. All this says is try not to make design decisions that unnecessarily prevent you from choosing another decision later on. Okay? So we would like to be able to keep as many alternatives open for future changes to the system as possible. And it's hard to come up with hard and fast rules for how to do that. It's just that every time you're doing a design, think, am I shutting off possible future changes? And finally, for flexibility, use reusable code, make code reusable. In other words, think about the previous two principles. Anticipate obsolescence. Another key principle that is not necessarily in relation to the other things we've talked about. I've mentioned this before in context of some of the risks sections at the ends of other chapters. The idea is that we want to avoid using bits of other systems that will run the risk of becoming outdated, forcing us to upgrade our system. For example, early releases of technology. It's probably not a good idea to be the first person to use a new programming language, or the first person to use a new graphical library, or the first person to use a new piece of hardware. Okay? Unless you can clearly see that you will gain a competitive advantage in the marketplace. So the costs really have to be less than the benefits. Just being the first person to use a programming language because it's cool when you could have used an older one is probably not a good design decision. Because the first people to use programming languages will encounter more bugs, and early releases of programming languages tend to have churn. Okay, so when Java came around, there were a number of things which were quickly deprecated in Java, and people quickly discovered problems, and new, better class libraries came out. A few years later, the language was much more stable. Okay, fewer changes. Same thing can occur with different hardware platforms. Okay, yes, you might need to go onto a new hardware platform in order to take the market for that platform, but don't do it just for the sake of doing it, because you're going to run into obsolescence issues. Another thing is to avoid using software libraries that are specific to environments. Okay, so if you come up and try to use a package that is Windows specific, that might be okay, an okay decision, because Windows has a dominant market and you sell plenty of products, but you are limiting yourself, and you won't be able to sell to people who use Unix, including the various flavors of Unix, such as Linux and Macintosh. Okay? You'll be limited not to use those platforms, and you might not want that. You might also limit yourself to the desktop instead of portable devices. So if you can find a package or a library that is more generic, that will be applicable to a wider variety of packages, such as Java, that's probably a good idea. And that's one of the big selling points of using Java, is that its libraries in general, not completely, but in general, are portable across a very wide variety of platforms, including all of the Unix flavors and of course Windows and many others as well. Another point is to avoid using undocumented features. Okay, I was guilty of this in the early days of my career. I was given a task to develop a number of systems, and I became a guru in a particular database technology and associated fourth-generation programming language. And when I left the organization, I left behind a bunch of code which used features of this database which were undocumented. Okay? I discovered them by trial and error, but they weren't in the documentation. Why is that bad? It's bad because if the features are documented, the vendor of that package will be perfectly justified in making changes and not even telling people of the changes. Hey, it was undocumented. We didn't say it even existed. So if you changed it, you used it at your own risk, and now you're going to have to change the system, and we're not going to give you any help because, hey, that didn't exist from the perspective of the vendors. Okay. Little used features is similar. Little used features, well, the vendors have documented it, but if it's hardly used, the vendor's not going to get too much pressure to be compatible in their next release of their library or the next release of the operating system. So you want to stick with features and libraries that are widely used by lots of people, because if they change, the vendor's going to have to support all those people. And there's going to be all kinds of other angry users demanding changes. You're not just going to be a voice crying in the wilderness saying that my feature doesn't work anymore. Okay? So I often wonder if the people who had to change this code that I developed years ago ever, started cursing my name for having used these undocumented features when they had to A, figure out how they worked, and B, adapt to new versions of the system that maybe, who knows, made these undocumented features obsolete or changed the way they worked. A fourth thing about obsolescence is to watch out for hardware or software that is produced by companies that you can't be totally confident in long-term support. Okay? So I think you can be pretty confident in using stuff that comes from the big companies, like Microsoft, or companies whose products are used widely in the industry. So for example, if Sun goes belly up, Java will still survive, because lots of other companies support Java and somebody will pick it up. But languages which are just produced by one company, there's a risk. Same thing with libraries or hardware that's produced by one company. In fact, when I worked for Nortel, one of my main jobs was to develop database systems whose purpose was to manage the use of electronic components and guarantee that in any design there were always multiple vendors of all of the electronic components that were used in those designs. So that if any vendor decided not to produce a component or went out of business, the Nortel would still be able to produce their products because they'd be able to buy the components from other places. So that's a fundamental part of any hardware company's business, and it should also be a fundamental consideration in software engineering too. Okay? Use languages and technologies that have multiple sources. The latest craze language is C#. It's a Microsoft language which is designed to build on some of the lessons learned from Java. It's very much like Java, but has some enhancements, and it's also integrated tightly into Microsoft's .NET architecture. Having said that, some people will be reluctant to use it because it is a single vendor, and therefore that vendor has a lot of power. Now, they're not going to go out of business, but they have a lot of power over you. You prefer to have something which has multiple vendors. The good news is that Microsoft knows this, and so there's also a version of the C# language that's produced in the open source community now, so you've got a choice. You can use the original or you can use the open source version. And Microsoft did that in order to stimulate the use of their new language. It's kind of funny. By giving away your technology, you in fact increase your sales of it yourself. It works. Okay? So, a lot of ideas about anticipating obsolescence. Often this principle is overlooked in design. It in many ways is as important as dealing with coupling and cohesion and abstraction, okay, and reuse. Design for portability is related to the above. Design for portability says we want to try and avoid tying our system unnecessarily to specific hardware architectures or specific software architectures. Okay? We would like to be able to take our system and plunk it on different hardware or attach it to different databases or different user interface toolkits. Okay? That means it's portable. Now, portability in Java is a lot easier. People who are programming today in modern languages have not a free ride, but a ride that's a lot easier than it was in the old days of C. Okay, and even C++, you know. Coding in C, you have to worry about the number of bits in the word and the endianness, the order in which the bytes occur in words, all kinds of issues like that. You have to worry about the operating system and how it's behaved with respect to a number of aspects of the calls you're doing. So portability was always a big concern in a lot of these languages. Less of a concern today, but still something we have to be concerned about. So try and avoid use of facilities that are specific to a particular environment. Try and use facilities that are generic and will work on many environments. Design for testability. Okay, what this says is, as we're designing our system, build in automatic testing from day one. In Java, there's a package called JUnit, which is becoming quite widely used today, which allows you to write your tests, your test code, right in with your program. Okay, and it asks you to structure your code in a certain way and provides drivers that allow you to run automatic tests. There are other strategies for building in test into your system. One of them is to use a layered approach. Okay, we already talked about the layered approach in terms of cohesion. It'll come up again in context of architecture in a few minutes. But if we have a functional layer that's independent of the user interface layer, one way of testing the system is to create a separate tester that plugs in the place of the user interface. It acts as if it was a user interface. Okay? And drives the system, calls all of our methods, does extensive testing automatically. Okay? Another strategy in Java is to write, which is simpler than using JUnit, is to just write main methods in all of your classes, or as many classes as you can, that will exercise the methods in those classes, so that you can test by just calling those main programs and run a series of tests. That's another strategy you might see quite often. The notion of design for testability is becoming more widely recognized in software engineering. It wasn't historically considered that important. These days, there are a number of movements in software engineering, particularly the movement called extreme programming or agile methodologies, that advocate, among other things, building testing right from day one. In fact, even building the tests before you actually write the code. You write the tests, then you write the code and see if it actually does what the tests expect it to do. It's a strategy that's becoming quite widely recognized in some contexts. Okay, and design for testability, by the way, has always been part of hardware design. Okay, all of the electronic systems are designed so that you can easily test them to make sure that the signals are the appropriate levels and things like that. But it's, in software engineering, it's a little bit of a newer concept, but growing in importance. Any questions about these principles? We've got one more to go. Okay, principle 11. It's odd to have 11 things in a list. Maybe 11 commandments. A bit odd. But anyway, we have 11 principles. The 11th one is design defensively. The notion of designing defensively is to not put undue trust in others. So if I'm designing a procedure, I will not trust that those who call the procedure will necessarily call it with the right parameters. And if I'm calling a procedure, I will not necessarily trust that the procedures that I'm calling actually work the way I expect. I like to make an analogy with defensive driving. When you're taught defensive driving, you're taught that as you approach an intersection with a green light, to not trust that some idiot isn't going to rush through the corresponding red light and crash into you. You drive slowly enough, you look, make sure that even though you've got a green light, that you still are on the safe side going through it. Okay? Or as you're driving through a neighborhood, you keep your eye out for kids running across the road. Things like that. Okay? Many other aspects of defensive driving. Basically, don't trust the other guy. And that's what we have to do with defensive design. We have to say, yeah, we have to assume that people will, generally speaking, follow the rules, but not blindly. We have to be open to the possibility that they may have problems. Now, some people use this defensive design as an excuse for not doing reuse. They say, well, we shouldn't trust the creators of reusable code. And that's a prime reason why reuse doesn't get done. Well, I would say, well, okay, if you're going to take that attitude, then you're not going to drive a car because you wouldn't trust that the car will not suddenly blow up, and you're not going to trust the traffic. You're not going to drive on the roads because you're not going to trust that people aren't going to be driving the wrong side of the road all the time. Okay, so you have to have a certain amount of trust, but you have to watch out for violations of that trust, whether the violations are accidental or on purpose. Okay, then the on-purpose ones could be hacking attempts and attempts to bypass security and so on. A lot of it goes accidental, just people making mistakes. So, never trust how people will use a component that you're designing. You want to, on the API of your package, you want to do checks for all of the arguments. Are the arguments the correct values? Okay, so if I'm expecting a value in 0 or greater, let's say I'm calculating the square root of something. Well, I won't trust that they're not going to pass a negative number. I will say, if the value, I'll only do the computation if the value is 0 or more. If I get a negative number, then I will throw an exception. Okay, I'm not going to blindly run into a crash just because somebody accidentally passed a negative number. Okay, so that's defensive design. But you don't want to do these kinds of checks in every method because that would be inefficient. If I'm passing this value from one place to another, I'm not going to check for positivity everywhere. I'm just going to do it on the boundary. Okay, I can trust the internals of my package, but I don't trust those things coming in from the outside. Otherwise, I get inefficiency. Design by contract is a methodology or a way of thinking that implements aspects of defensive design. Okay? Design by contract says, imagine that every single procedure that you create has a contract with its callers. This contract will specify a number of things. Preconditions, which are those things which the caller guarantees to make true when they call you. Postconditions are the flip side. Okay? Every contract has gives and takes, right? Make an agreement, I can give you something, you give me something. So, what you give me is the preconditions. What I give you is the postconditions. Okay, so the postconditions are my guarantee of the integrity of the data that I'm passing back to you afterwards. Or I guarantee that I will have done some calculation correctly. Invariants are those things that we agree we will not fiddle with. Okay, so invariants are things that will not change, and we both guarantee that they will not change during the execution of this procedure. Okay, so if you systematically design all of your procedures, or all of your method handlers, or your message handlers in servers, for example, same concept applies. By thinking about the preconditions, the postconditions, and the invariants, you're doing design by contract. You're considering that everything has a contract with its users, with its callers. This notion was invented, or implemented at least, and popularized in a programming language called Eiffel, which is still reasonably widely used today, and is one of the important landmark object-oriented programming languages. And obviously, it's nowhere near as widely used as Java and C++, but it still has a decent dedicated user base in a number of companies. And it builds in these notions. You can code up these preconditions, postconditions, invariants as logical statements in a language that looks a bit like OCL. Okay. If you're doing this in Java, what you can do is you can have logical statements at the beginning that will say if logical statement, then throw an exception. So they will trap any violations of any of the preconditions. And upon return from a call, you can check the postconditions in the same kind of way. In C++, there's a package called the assert package that allows you to do something similar. Okay? So that brings us to the end of our list of 11 fundamental principles of design. Your objective is that as you're doing design, you constantly evaluate, am I adhering to these principles? And if I'm not adhering to them, why not? There could be justifications. Okay, there's always trade-offs. But I want to see if I'm adhering in general to the principles. Any questions? Okay, I want to spend a few minutes talking about overall strategies for making design decisions. We talked about this notion of design decisions as being what you make when you have an issue, you have several options, and you have to decide between the alternatives. We want to do this in a systematic way. The systematic way involves thinking about priorities and objectives and making the decision which will best meet those priorities and objectives. And also, if we can, we do a cost-benefit analysis. Now, this approach, making decisions effectively, is taught in business school. You might learn it in a business course, and you might learn aspects of it in a project management course. So I'm not going to go into it in a lot of depth, but I want to give you a flavor for this process so that you realize that when you're doing design, you should try and make decisions in a systematic way. Document your decisions so that people can see the rationale you used in making those decisions. So first of all, I've got to have some priorities and objectives set up. These come out of the requirements, and they can evolve over time as well. First of all, we want to list and describe the alternatives for decisions that are important. You don't have to do this for every decision, but for important decisions, you want to do this. List and describe the alternatives. You did that in your requirements document, so requirements are done in a similar way. You want to list the advantages and disadvantages of each of these decisions. Again, you did that in the requirements. You can show these as a table. We'll see that in a minute. Sometimes some of the alternatives completely prevent you from making certain decisions. Okay, they rule things out. We'll see that. Beyond those, you have to balance the pros and cons and come up with a decision that has more advantages than disadvantages. Okay? And finally, sometimes the priorities will change as time goes on. So for example, if I've made a number of decisions early in my design process that have an impact on efficiency, okay, efficiency might not have been that important, but if I start making decisions that are inefficient and consume a lot of CPU resources and memory early on, later on in design, I might be short of memory and CPU time. So efficiency might become more important in the latter stages of the design process. Okay? Or conversely, I might have made some decisions early on in the design process which result in very efficient design. Okay? So later on in the design, I can do some design decisions that are a little bit less efficient because I've got plenty of CPU and memory to spare. Okay? So these priorities can shift as we make decisions. Here's a scenario. Imagine that I was designing a system, and in conjunction with my customers and users, I discussed that I had the following priorities. Job 1, security. Essential to have security in this system. I'm going to quantify it. Where possible, I want to quantify all these things. I'm going to say that, well, let's use a 400 megahertz Intel processor as a baseline and say that, well, you know, all my work's going to be done within a few hours. So if a hacker's going to spend 100 hours hacking, they won't be able to damage anything that's going on here. Now, obviously, this slide was put in a few years ago, so we have to adjust these things now. 400 megahertz is a bit passé, so I might have to improve my security constraints now. But anyway, we've tried to quantify it in some way, and so I'm putting that as top priority. Second priority might be maintainability. I'm not giving an objective here. I'm just saying pay attention to maintainability because this is a system that will undergo a lot of change. And I have to evaluate maintainability on a case-by-case basis. CPU efficiency is reasonably important. Not as important as the other two, but reasonably important. And I'm saying that response time must be within 1 second and that I have to assume that some users will be on slow machines. Okay? Network bandwidth efficiency is next in my priority list. I have to try and limit my bandwidth, and I've said to myself that given all the other traffic that's going over this network, and given the volume of transactions I have, I'm saying to myself that I should try and limit myself to 8 kilobytes of data per transaction. So I might have 1 million transactions per day or per hour, and if I go above 8 kilobytes per transaction, I'm going to be overloading my network. Okay? Memory efficiency. Okay? Less important. I can upgrade memory, so it's less important, but given the total number of applications running on these computers today, I might say I want to limit this to 20 megabytes for this particular one. By the way, these lower priority things are things which I have relatively low cost solutions. I can upgrade my network if I have to. I can certainly upgrade memory easily. Memory is so cheap today that it's usually not a big deal. So, I mean, it looks a bit ridiculous to limit yourself to 20 megabytes today when I can buy 256 megabytes for $50, you know. Anyway, who knows? Maybe this is on an embedded system running in a small device somewhere. Portability is another issue. They put this as a lower priority and basically saying, well, it would be nice. All right? So given those priorities then, what if I had 5 algorithms that I wanted to choose between at a certain point in my design process? I can evaluate them all according to these priorities. And I notice right away that my top priority security, algorithms A, B, and C, that's fine. Algorithm D I don't know. I'm not sure. I'll leave that for now. Think about it later on. Algorithm E doesn't meet the security requirements, so we abandon it right away. Okay, then moving on down the list. Maintainability suggests I should use algorithms B and C, although memory efficiency, which is next, suggests I should use A and C. So C looks pretty good right now. But perhaps B behind that, perhaps A behind that. I haven't really thought about D yet. CPU efficiency. Well, this is bad. CPU efficiency, none of these algorithms meet the objective. Okay, I cannot meet the objective I've set for myself, so I have to adjust my objective. Okay, well that was a relatively low priority thing, so I can require this run on faster machines. But nevertheless, I noticed that algorithm C, which was by that point was leading the race, it says that it's low efficiency. It's particularly low efficiency. So that might tilt me, even though CPU efficiency is lower in the priority list, it might still allow me to think possibly about algorithms A and B as being possible alternatives. Okay. So I still might choose algorithm C because it's high, high, high for the first three, but I might just have further discussions with my clients about algorithm B, which has better maintainability, okay, and higher CPU efficiency. Okay. So this is one way of looking at and analyzing some aspects of our designs, and this is primarily here done in a qualitative way. Not too much quantitative, not too much data analysis here. I can, if I want, move on to a more formal mathematical approach, a true cost-benefit analysis, where I add up in dollar terms all the costs and all the benefits. And this is something which anybody who is doing a management role needs to learn. In software engineering, I need to think about all my costs, and these costs include the amount of work that's done, the software engineering work that will be involved, the development technology, so the programming languages, the database technology, any other tools, libraries I have to buy for myself as a developer, and copies that my clients have to have. It's all costs. And the incremental costs in terms of end user costs. So maybe one approach would require the end users to take more time in their work because of efficiency concerns and longer response times. Or product support. Maybe one approach would require ongoing intervention by product support teams to help support the application, whereas another approach wouldn't. Okay? So all these things are costs we have to consider making a decision. And then the flip side is the benefits. Okay? How much time are we going to save ourselves in our development organization, which we can then pass on as lower price? And secondly, how much benefit are the end users and clients going to have in terms of lower operating costs or lower purchase costs that we can pass off to them, or increased sales that we can make by having a better product, which is ultimately a benefit to ourselves. Okay? So we have to add all these things up. We convert them to dollar figures, okay, considering all aspects, and it's quite a complicated business to think about all the aspects. For example, how much does a person's time cost? It's not just your salary, it's your benefits, your office space, your management support, your secretarial support, your vacation time, all those things all add up. So your salary is a small part of the total cost of having you spend your time. But anyway, in the end, we add all these things up and we ensure that the benefits outweigh the costs, as well as having all the other issues such as security and so on dealt with. In fact, we can quantify things like security. What is the cost of a breach of security? What would it cost if some hacker got in and got our data? We can quantify that, hopefully, in some way, approximately at least. And then we can say, well, we want to spend money on security, but we don't want to spend more money on boosting security more than the harm which would come if a hacker got in. Okay. All these things have to be weighed. Any questions? Okay? This is a taste. The idea being that you're going to see more of this stuff in other courses, or whether they be in the University of Ottawa or later on when you get out into industry. But you need to understand the underlying principle at this point. Okay, let's talk about software architecture now. We've talked about a number of aspects of software design. We've talked about class design. We've talked about user interface design. We've talked about techniques for design like state diagrams that can be applied to many aspects of design. We've talked about design principles. Software architecture is one of those areas of design that you can specialize in, like UI design, like class design. Okay? It's the area of software design that has to do with the large-scale issues for putting systems together. So how do I group together components and modules and so on? It involves dividing software into subsystems, deciding how those subsystems communicate with each other. So maybe it's client-server, maybe it's calling procedures. There are several other ways. And determining the interfaces between those various components. As we'll see in a few minutes, there are a number of different styles we can use, such as pipe and filter and client-server we looked at, and a number of others that we'll see. What you want to do when you're doing the architecture is to build a piece of the document, or a document as a whole, that's called the architectural model. This document is a document that everybody who's working in this system will refer to from time to time. It will serve as a roadmap, okay, for the entire system as a whole. So they can see where their piece of system plugs in, how they communicate from their part of the system to other parts. And it will be a constant referral document for everybody. Not everybody will look at the details of each part of the system, but everybody will look at the architectural model. It will allow the project managers and the high-level people working in the system to divide the system up and allow people to specialize. It will also allow you to imagine how you would extend the system. Quite often, in an architectural model, you show an architecture that looks something like this. Various different components that talk to each other. And then maybe you have ... some other components, and you say, well, in future, we're going to allow for these components to be plugged in. We're not doing it yet. Okay? So they facilitate reuse and reusability. So slide 55 sort of summarizes some of the things which you want to put in an architectural document. I'm not going to go into it in a lot of depth. The breakdown into the subsystems, the interfaces among those subsystems, the dynamics of the interaction. So you might need to specify, say, a state diagram model for this interaction, or sequence diagram to show the protocol, messages sent backwards and forwards. The data that will be shared, it might be that all of these various components are going to be accessing a database and sharing data among themselves. It might be also that we have a number of pieces of hardware involved, and so different pieces of this system will be plugged into different pieces of hardware. Okay, so I might, for example, have a couple of components here that talk to each other that are put on the same piece of hardware. Okay, and in UML in a few minutes we're going to see that I can show hardware designs by using a three-dimensional box that looks something like this. Okay, I'm not very good at drawing these three-dimensional boxes, but it's going to look something like this. Okay, so that's saying that these two components are inside this piece of hardware. Okay, so this is the typical picture of the very high level what an architecture might look like, and later on we're going to see some flavors and variations on that. Obviously you label these things and give a lot more details, but this might be the top document, the top vision that everybody has of the system. We like our architecture to be what's called stable, meaning that it is not going to be changeable very easily. I mean, we'd like to be able to change the system easily, but that change is made without needing to change the architecture. Okay, we don't make the architecture deliberately so that you can't change the system, but we make it so that it doesn't need, the architecture resists and still survives even if we add new features and change the way the aspects of the system work. That's what stability means. A number of issues to do with developing an architectural model, okay? Sketches, rough sketches like this on the board are a good way to do things. Working in front of whiteboards or blackboards is a good way to have a team of people work out the architecture. You might need to think about architectural patterns and sketch out alternatives using the patterns we'll talk about in a few minutes. And finally, another strategy is to have different groups of people in your organization work independently on each architecture, on the same architecture. So I might have you folks sit down and work on a version of the architecture. Have this group here do another architecture, this group do another architecture. Then I have 3 architectural models, all developed within 2 or 3 hours of work, sketching out on boards in different rooms. Then everybody gets together and looks at and compares. You might find strong similarities, and that's good because it shows that you think alike, and you've probably got the right answer. But you'll also notice differences, and those differences then can be subject to analysis, which is the best approach. Okay? So this notion of parallel design is a powerful notion that we can do. You don't do parallel design for the entire system very often, with all the design and coding in full detail, because it's very expensive. But spending a few hours having different groups working independently and then come together can be really an effective way of making sure you've got a good architecture without forgetting things. Okay, questions? Okay, you're going to refine the architecture as time goes on, adding details. Maybe you have a top-level architecture, and then this component itself has an architecture, and so does this. Okay? You also will typically think of architectures in the context of use cases. As you're developing the architecture, you may very well think of the use cases. One use case, for example, might just interact with this component. Another use case might interact with this one. Another use case might do some stuff that involves all these components and then go back to the user. Okay? And so thinking about the use cases that are important and what architectural components are needed to support them is a recognized way of working out an architecture that does what you want and doesn't do anything more than what you want. Avoids you coming up with an unnecessarily complex system. There are a number of diagrams which we'll see which extend UML specifically for architectural diagrams. We're going to see 3 of these right now. The first one is the package diagram. Package diagram is a box with a little tab on the top. Okay, I could have shown these things here as packages if I'd wanted to, if that's what they are. Okay, a package is a grouping of things in UML. In this case, it's a grouping of other packages. But this picture of OCSF and Simple Chat, inside the client is going to be several classes. Inside the server and the common part are going to be several classes too. This is familiar to you because you've seen this notion in Java. Java implements directly the UML notion of packages. Okay? It turns out too, though, that in UML I'm allowed to group other things in packages. So I can group sets of state diagrams or states in packages. I can group sets of hardware components in packages and so on. I can group anything in a package in Java, in UML. In Java, it's groups of classes. You'll notice also that there's a relationship. I can have relationships between packages. In this case, the imports relationship, as in Java. But I can have others if I want. Slide 61 is illustrating something which you don't have to learn and memorize, but I'm illustrating to you that the UML goes significantly beyond the details that we've seen. They define, for example, the notion of a subsystem. A subsystem is a special kind of package designated by having this little fork symbol near the top. And I'm showing the package divided up into 3 main subcomponents. I have my specification on the left, a list of methods in the API first, and then below that a use case diagram, so showing how this subsystem will be used. And on the right I have aspects of the realization or implementation of that, the class diagram, perhaps a state diagram, and so on. Okay? So just to show you where package diagrams can be taken beyond the basic box with the little tab on the top. So there are many, many aspects of UML that you can specialize in as you become more advanced in software engineering. Second major kind of diagram that can be used to describe architecture is the component diagram. Remember, we talked about components the other day. They are pieces of implementation that you can plug in to build a system. You can typically replace them and you get the same system. Okay, they have an interface. They're implemented. So here we have a client component and a server component. The notation is the box with the 2 little tabs sticking off the left-hand side. That's the standard notation. And as with other UML symbols, we can have relationships. So in this case, we're saying the client communicates with the server. There's a communication relationship with them. Okay? So very simple diagrams, just illustrating slightly different notations, different ways of grouping things. And finally, we have the deployment diagram. Deployment diagram is a chunk of hardware. I showed that here already. Okay. By the way, this could have been a component. Two little boxes. This thing here is a chunk of hardware, often called a unit, and inside it there are several packages. Maybe I should have instead called these components. It's normal that you have components inside a piece of hardware. The idea is that we're saying where the software will be installed. Okay? In this case, I'm installing these two clients on machine 1. Maybe I have a machine 3 down there which has other clients on it. I'm saying that machine 2 has a server, and there's also a chunk of hardware that I'm not talking about the innards of it at all, the GPS satellite. Okay? And I'm showing the method of communication among these pieces of hardware too. Any questions? Okay. Let's move on then and talk about architectural patterns. We talked about the notion of patterns in general back in Chapter 6, design patterns. So we had the proxy pattern, and we had the facade pattern, and the abstraction occurrence pattern. The notion of things which are recognized pieces of wisdom that you can reuse in your designs. Architectural patterns are the same, but they're applied at the architecture level. They're also often called architectural styles because the notion was in use before the word pattern was invented in software context. Okay? The first few patterns I'm going to skip over very fast because we've seen them before, but I want to remind you that they are in fact patterns. The multi-layer pattern. The concept here is that we're going to divide the system up into units, typically components that have layer cohesion. Okay? Each layer has a well-defined interface that's accessible to higher level layers. We saw that before. This diagram, slide 66, was also shown back earlier on in the chapter when we talked about layer cohesion. Here all I'm doing is I'm showing these things as, in this case, packages that access lower level packages. Okay? So this is layer cohesion. This is the architectural style. Whenever you see systems organized this way, you know that it's following the multi-layer pattern. And in general, the multi-layer pattern dominates software today. Most systems have layer design somewhere inside them. Okay, whether it be just the user interface separated from the functional layer. All right? Now for each of these patterns, I'm describing a series of the design principles. Remember the 11 principles? Well, each pattern gives rise to benefits that relate to those 11 principles. So for example, multi-layer is a way of dividing and conquering. It gives you layer cohesion. It reduces coupling because the coupling is only calls from above, one directional. Okay? Each of these layers is an abstraction and is, especially at the bottom, they can often be reusable. They can help you to deal with portability issues, for example, because I can isolate the access to my database or the access to my operating system in layers. So they all benefit a number of these types of design principles. For the rest of the architectural styles, I'm not going to go through this list in detail. Okay? They're on the slide, you'll just have to read them yourself or look at the book. Okay? But bear in mind that each of the architectural styles gives rise to particular benefits and, so in some cases, particular drawbacks. The second architectural style or pattern is also one we've seen and we've spent considerable time on in this course, the client-server architecture. Now, I'm generalizing it here, the client-server and other distributed architectural patterns. The concept is that there's got to be some component which has the role of server, could also act as a client as well, and a number of other components that act as clients. They could also act as servers as well. And that we have communication lines between them using protocols. Okay? The way of dividing up a system so that that happens is this pattern as a whole. If we have everything acting both as client and as server, we call it peer-to-peer. If we have strict differentiation between clients and servers, we just call it plain vanilla client-server architecture. Okay? But the idea is that we're doing something different now. Before we were dividing these up into layers. Now we're dividing these up into clients and servers. They go together because we can divide our server into layers, we can divide our client into layers. But they nevertheless represent a different way of dividing up the system. On slide 70, I'm showing a number of, in this case, components, shown with these two little tabs on the left. A main server, which can be used by various clients to look up addresses with these communication links. And then the clients that can exchange messages among themselves. They aren't pure clients because they can directly communicate with each other. Each of them is also acting as a server. So these three things on the left represent a peer-to-peer type of communication. But the communication to the server on the right for address lookup seems to be pure client-server here. You can have big networks of these things all connected to each other, following this architectural style. Any questions? Okay. Again, we have pros and cons. I'll let you look at that. The third pattern we'll get to in slide 73 is the broker pattern. The broker pattern builds on top of the proxy design pattern that we saw earlier on. It allows us to work with an object locally and then to go out and get a bigger object over the network at some point when we want to. This architecture is implemented in using a number of frameworks. One of the more common ones, or one of the ones that's most well known, is CORBA, Common Object Request Broker Architecture, which is the subject of more advanced software engineering courses here at the University of Ottawa. Microsoft has a number of their own implementations of the broker architecture. Some of them relate to its new .NET initiative, and there's some older ones as well. So here's an example of the broker in action using a diagram involving components. I have a client which internally has a proxy object. Remember the proxy pattern. So we can do things with this proxy object, but every now and then I have to access the heavyweight. How do I do that? Well, I go out over the network. Now instead of accessing this remote object or this heavyweight object directly, I'm going to use an intervening server. Okay, so this is, by the way, using client-server indirectly. Each of these things is using client-server communication. But the broker is a special kind of server. It's a kind of server that knows where other servers are located, and it knows where objects and data is located on the network. So instead of my client having to access and know about all of these things on the network directly, it just asks its broker to get me the data it needs. And the broker then goes out and finds the information for the client. The advantage is that I can change these remote objects. I can change those servers, I can shift them around, I can provide alternative services for that data without having to change the client. All I have to do is to tell the broker where things are. So multiple clients can access the broker to get these remote services and all the clients don't have to know about all of the services where they all are. The broker intervenes for them and helps them get access to things that can move around. Okay? So it's like, instead of contacting 100 insurance companies to get a quote when I want to buy insurance, I contact a broker, and the broker goes and gets all the quotes for me. So I have one point of contact. Okay, so a very powerful way of structuring systems that simplifies architecture considerably. And again, there are some ways in which this architecture gives us advantages and disadvantages in terms of the principles we talked about. The final pattern I want to talk about today is the transaction processing pattern. This is a pattern that dates back to the early days of computing, where what you did was you read in a series of inputs one by one, call them transactions. They might be debits and credits to a bank account, for example, or transfers of funds or payments of bills. Process them as a series, and I pass, as each one comes in, on slide 77, I pass that to a transaction dispatcher that chooses which component of my system will deal with the transaction. Now, the transaction processing architecture is often implemented simply as procedure calls. Okay? Procedure calls, I have an input processor that reads from a file or reads from a terminal or an ATM communication line, passes it to a transaction dispatcher that then calls the appropriate procedures to interact with my bank account. But these could also be implemented using separate components communicating over a client-server architecture. So as you can see, all these architectures go together. I can have client-server here. I've got communication. I've got transaction processing, and there's also a tie into the broker architecture. You'll notice that this pattern looks a little bit like the broker. I've got something in the middle that is intervening for me, that is helping decide what to do. So the broker was helping decide where to get data. The transaction dispatcher is deciding where to process requests. There is a similarity between the two, for sure. Okay. So we'll pick up with the rest of these patterns and move into testing next day.